Hi everybody, and welcome to example 6 on page 44 of the workbook. Let's take a minute to read this example together. So for each of the following linear transformations t, we'd like to find the rank and the nullity of t, and then to decide whether t is 1-to-1 and whether it's onto. Okay, and these theorems that we've been talking about are going to be very useful to us in answering this question. Okay, so let's start with the rank and the nullity part of this. I'm going to start with by finding the null space. Okay, and remember that's like asking what's the set of all input vectors x1 and x2 that would produce an output of 0, 0. Okay, and notice that in this particular case it leads us to a pretty simple system of equations. x1 has to be 0 and negative x2 has to be 0. Okay, in matrix form that would look like x1 plus 0 x2 is 0, and then 0 x1 minus x2 is equal to 0. If we reduce that, there's not much to that. We're going to get that, and notice that we have a pivot in both of the two columns. Okay, but what that means then is that the only solution to this is x1 equals 0 and x2 equals 0. Okay, so here's what we can say then. Since the only solution to this system is x1 equals x2 equals 0, okay, we see that the null space of t is equal to just the 0 vector. Okay, that's the only one that works according to our calculation. Okay, what's nice about this is that just by doing that one calculation, we actually have enough information to answer this whole question if we play our cards right, if we use the theorems that we have. Okay, so the first thing that we can say is the nullity of t is 0. Okay, and that's basically because the null space just contains one vector, the 0 vector, and a basis for that vector space is just the empty set. Okay, so we've got 0 vectors in a basis. That means the nullity of t is 0. And we can then figure out what the rank is by using the dimension theorem. Okay, let's recall kind of what the dimension theorem says. It looked like, I'm just going to sneak that in up here, the dimension of v equals the dimension of the null space plus the dimension of the range. And remember, this v was basically the domain of our linear transformation. So the v that you see here is really R2. Okay, so if we take that theorem and just rearrange it, that means that the dimension of R of t, okay, otherwise known as the rank, is equal to the dimension of R2 minus the dimension of the null space. Okay, if we just kind of rewrite that equation, the dimension of R of t is really just the rank of t. And we know that the dimension of R2 is 2, and then by definition, dimension of n of t is the nullity of t. All right, and we calculated the nullity of t right here. We know that it's 0, so the right-hand side of this equation is just 2 minus 0, which is 2. We've just figured out what the rank is. Okay, so what's left to answer here? We just calculated the rank and the nullity. Now they'd like us to decide whether t is 1-to-1 and onto. Okay, let's do the 1-to-1 part of this first. Okay, we calculated the null space and discovered that it contains only the 0 vector. And so by theorem 2.4, t must be 1-to-1. Okay, again, because the null space just contains the 0 vector. We did that calculation and verified that. Okay, and what about onto? Okay, well, there's kind of a sneaky way of convincing ourselves that this is onto. And it starts by noticing that the dimension of the domain and the codomain are the same. Okay, they're both R2. And recall what theorem 2.5 says. It says that if that's true, if the dimension of v and w, the domain and the codomain, are the same, then t being 1-to-1 is equivalent to it being onto. So the fact that we demonstrated that T is 1 to 1 means that it's also onto. Okay, and so that's going to be our last comment here by theorem 2.5. T is also onto. All right, so the thing to notice here is how helpful the theorems were to us. We had to do relatively little calculation here. Just calculating the null space allowed us to kind of figure out the rest of the things they wanted from us relatively easily.